Welcome back, students. We nearly completed section 2, but we have one more topic to go, general solutions. And general solution of an ordinary differential equation have various forms, but all the time we have undetermined parameters. This is an example of a second-order ordinary differential equation with the general solution here, and we have two constants, capital A and capital B, which are highlighted in blue and red respectively, and these can be arbitrary. Depending upon those values, we have various possible solutions, and we can determine those with appropriate initial condition, which will be considered in section 3, by the way. And as far as checking the solution, it's not too difficult. Oh my, I didn't do it. I have just mathematical computation here. A to the t power, b t to the t power, and then take second derivative minus twice first derivative plus original, and then yeah, that's 0. So here's the checking process there. As for manual computation, well, I'll leave the details to students. Derivative of this a part is a times e to the just t power. And then here's a product rule. So and so on. Get the second derivative and plug those in and see if you really have 0. I'll leave the details to the students. Here's another example. And let's see, this example is essentially the same example as this one, except this is constant. And then what did you do here? In this example, we simply took from here, which I'm highlighting green, I took the derivative implicitly and I got 0 because the derivative of any constant is 0. And bring it down over here. And this is just r squared. This has to be positive, so arbitrary constant cannot be just real arbitrary. If it is negative, then it doesn't make any sense. So I put r squared so that I want to emphasize this is positive constant. And then take the derivative, whatever that is, we get 0. So exactly the same as before, and you can easily check whether this is a solution. And depending upon the r value, the radius of the circle, by the way, we're going to get various solutions. And that family of solutions is called the general solution. And here a couple more. This a value can be various, that b value can be various. Okay, those are general solutions. And among those general solutions, sometimes we have additional conditions to identify those constants, and we get down to a unique solution, or at least very small number of solutions that we want. Or sometimes a solution that we want and the solution just tags along, which is actually problematic, but we may have to consider it anyway, which we call singular solution. Let me show you various examples. Those kind of things are initial value problems. Differential equation is here, and then initial condition given by y of t0, y prime of t0, y double prime of t0, and so on and so forth. Most of the time in physical example, t0 is the time that you begin the measurement. And if you're free to choose your time, then most of the time you're going to select t0 as 0. So at time 0, we have something, 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 all the way over to the nth equation. Well, here's a bit less general form when y to the nth power is explicitly sought, but this is a little bit more general case. But in any case, those kind of things are called initial value problems. Here are some examples of initial value problems. we have a differential equation, y prime is equal to y, and we have an initial condition, y of 0 is 3. We have the same differential equation, but I'm given different initial condition this time. Y of 1 is negative 2. Even though we have the same differential equation, we have two different initial value problems. This is one problem, and that's another problem. So we have to look at those as two separate problems, actually. So, shall we check and analyze? Okay. I claim the general solution is c times e to the t power. Can you check? That checking is now left to the students. I gave you several examples already, so you should be able to do that. Now, let's work on initial condition. So for blue problem, what do you get? Y of 0, which is c times e to the 0 power, had better be 3. So what is this c value? What is e to the 0 power? What's e to the 0 power? That's 1, isn't it? So we have to have c is equal to 3. Now c is equal to 3, that's not the end of the problem. What we're looking for is y of t. So at y of t, c is equal to 3. So what do you have? Y of t is equal to 3 e to the t power is the final solution. And this is the solution of this initial value problem, the blue problem. How about the red problem? Similar. Same general solution. Y of 1 is negative 2. So y of 1 is c times e to the first power is equal to negative 2. And what is this? C has to be negative 2 over e. Therefore, y of t is equal to negative 2 over e times e to the t power. Let me write it like this. Instead of e down here, let me write it as e to the negative first power. Oops. So instead of e down here, let me write it as e to the negative first power. In that case, it is a little bit easier to simplify. T minus 1 power. So this is a solution of the second initial value problem. So same general solution because we have the same differential equation, but we have two different initial conditions. Therefore, we have two different solutions. Okay. Here are solutions, they match. And by the way, here's a visualization. So these gray curves are part of the general solutions. There are infinitely many, of course, because C can be arbitrary, but I selected some, and we have these. And then blue is given by this initial condition, which is highlighted in blue right here. At t equal to 0, y value is 3. So we have 0, 3. Do you see? This. The other one is 1, negative 2. When t is negative 1, y value has to be negative 2. It's right here. Does it make sense? T equals 1, and that's negative 5. So this is about negative 2 vertically. Yeah, it makes sense. So the curve that runs through this point. There are infinitely many curves because the family of solutions, or the general solution, is infinite. But among those, we can select specific solutions given by initial conditions. In both of these instances, each initial value problem had a unique solution. Blue had its own solution, red has its own solution, and the visualization confirmed those. Is everybody happy with this? How about the next example? Can you do this on your own? Well, I'll help you just a little bit. Okay. What's the general solution? I'm pretty sure we already saw it. Have we? No, we haven't. No, we haven't. Actually, I should have given you that. Okay, all right. So here we go. Start from here. The general solution is 1 over t squared minus c. How to find this general solution, that's the topic of next week. We have a technique called separation of variables, and we can use this kind of technique to actually find it. But that's something we're going to do next week. So here's the general solution. And depending upon the c value, we have infinitely many possible solutions here. Okay, we have 3 initial conditions, so we have 3 separate initial value problems. They all share the same general solution, yeah, but let's find those out. Plug in t equal to 0. 0 minus c is equals to -1. So c is -1. Is that what you're getting? So plug in 0, that's 0. So 0 squared, so that drops out. 1 over negative c is -1. C has to be, no, c has to be positive 1, excuse me. Therefore, y of t is 1 over t squared minus 1. You happy? How about the next problem? I'll leave the third one to you. Next problem, y of 2, which is 1 over 2 squared minus c is 1/3. One over 4 minus c is equal to 1/3. I have c equals 1. Did I do this right? 4 minus 1 is 3, okay. So I'm having y of t is equal to 1 over t squared minus 1, same as before. And I'm going to leave the third one to students. So what do you have? Stop this video and do it on your own. So if you do it right, what do you get? With these, oh, they're all the same. They're the same. Did we? As a matter of fact, no. They share the same expression, yes, that's true, but they all have different intervals of definition. Here's the tricky part. Different intervals of definitions. How can you tell? Well, the best way to tell is to see the answer. So I'll show you the answer. Here comes the visualization. Ready? So blue, red, and green corresponds to 3 different curve segments in 3 different intervals. From negative infinity to -1, we have this green. From -1 to +1, we have blue. And 1 to infinity, we have red. Now that you saw the visualization, you have the idea. Let's go back and look at those solutions and pretend you don't see this graph and try to answer what are the intervals of definition. Let's see. This expression makes sense whenever denominator is not 0. So denominator is 0 when t squared minus 1 is 0, so we have 1 or negative 1. And positive 1 here and negative 1 there. There we have two vertical asymptotes. Okay. Now these two singularities divide the number line in 3 pieces. And those 3 pieces are unrelated to each other. They are not related to each other. And blue condition here, blue initial condition here, corresponds to the interval in the middle, negative 1 to positive 1. Let's see. So we have y equals 1 over t squared minus 1. Then t should be a member of negative infinity to negative 1 or negative 1 to positive 1 or positive 1 to positive infinity. We have two singularities, negative 1 and positive 1. That's where denominator is 0. Therefore, we have 3 intervals. These two singularities divide the number line in 3 pieces. And we have 3 intervals of definitions. And depending upon which initial condition is given, we have to select appropriate interval definition because these 3 intervals of definitions are unrelated. So, first condition, t equals to 0 is given, so that corresponds to the middle, blue. The next problem, t equals to 2 is given, so that corresponds to the third interval. Final piece, negative 3/2 is given, that corresponds to the first interval here. Green, blue, red, respectively. They have 3 different intervals of definitions. They are unrelated. By the way, students who skipped lesson 1A may wish to go back to this topic and review a little bit. Piecewise differentiation and integration here. Believe it or not, the given calculus is wrong. Correct it. Antiderivative of 1 over x is log of x absolute value. What's wrong with that? In calculus 1 it was correct, but in differential equation, not entirely correct as a matter of fact. We have singularity there, x equals to 0, so we have log function, singularity. So log of x or log of negative x, depending upon whether x is positive or negative. Now we have 2 integral constants, plus a plus b. They are unrelated. Even if I have 2 different constant values here, take the derivative and you're going to get 1 over x, you see. Here's another example. Singularity is x equal to 0 again. So we have 2 different constants in 2 different intervals. So piecewise integrations are a little bit funky. We have singularities, so we have piecewise defined function here, and each piece behaves differently. Final problem here, I'll leave that to students. General solution is this. General solution is that, okay, and then determine C using these initial conditions. Good luck.